So hello everyone, and welcome to our tutorial. And our topic today is KataContainers, the hard way. And we will basically talk about Kubernetes with Containerd and KataContainers. And we will give you a live demo, your basic knowledge about how this kind of system works and what's the benefit of it. And we also talk a little bit about the difference between the different kind of secure containers. So I am Lei Zhang. I came from Alibaba Group, and I previously working for HyperHQ. And I'm a co-maintainer of Kubernetes and once a member of HyperHQ KataContainers team. And my colleague is Wang.
Hello, I'm Xu, and I'm the co-founder and CTO of HyperHQ, and also we are one of the initiator of the KataContainers project. And so today we will have first we will have a brief introduction about the KataContainers itself, and then they will go through the CRI part, and then we will begin to connect the KataContainers and the Kubernetes and some future works. So time to begin?
Yeah.
Why? Yeah. So firstly, I will introduce about KataContainers. KataContainers is it's a 1-year-old project, and last year in the Austin KubeCon we launched this project. And last week we celebrate the 1 year birthday of KataContainers. But at our booth we still found some audience still not know well about what Kata is. Actually, KataContainers is a container runtime, just like runc, in the same place of runc, and works in almost everywhere runc works. So in brief, it's a container runtime, and it follows the OCI specifications. And but the difference is it's built with the virtualization technologies, just like a VM. So from the host, when you run KataContainers, you may find that there is a VM in your host, but from the applications view, itself is a container. And the project first initiated by our HyperHQ and Intel, and hosted in OpenStack Foundation, and also have other contributions from Huawei, and Google, and Microsoft, and Alibaba. Sorry, I don't list you. And yes, in one sentence, KataContainers is virtualized container. And here's a brief comparison between the runc and the KataContainers. And for this part, the runc, when we use runc, we have the process for the applications, and they are protected by the something like SICOM and some other things to help to isolate from the from others, and use namespace to do the isolations, and also C groups. And but all the container processes run on the same Linux kernel, and depend the C groups and namespace do the isolation things. And once there, every year there is some CVEs against the kernels, and there always be some bad CVEs. Then they may avoid the isolation of the namespace, and maybe ICD Linux and other things, and they got to have the privilege of the host. And in the past year, we have tried to do some demo about this. And when we have some hacked kernel, we can some past version kernel, such as 4.13, and there is a CVE, and we use that to just break the runc and get the control, all the privileges of the host and other containers. So at this point, if you want to have a more secure isolation for your containers, you must have at least 2 levels of the isolations. So that's the idea of the Linux of the Kata containers. We use the virtualization, and then we run every sandbox, every pod sandbox inside actually a virtual machine. And the process inside the gas kernel, there is inside the virtual machine, there is a small gas kernel, and even if they can do the exploit in the guest, they cannot escape to the outside. So this ensure a better isolation than the runc container. Here I'm not saying that's absolutely safe, but it's a better isolation. Yeah. Yes. Sorry.
Do you need to have this 2-level virtualization?
You mean to compare with the cloud providers?
Let's say AWS.
That's I don't know whether I understand your question correctly. You mean we are an open source project, so we used by if you run on the baremetal things, your containers run in a gas, then the position of your container is just like an instance of the EC2 instance. If you have further questions, we can have discuss after the session. Right. Okay. And this project, actually, we have 2 similar projects from HyperHQ, the RunV, and from Intel, the Clear Containers. The 2 projects all began at May 2015. So, and we launched almost in the same month, actually in the same week. So before that, for me, I don't know Intel has such a project, and for Intel, I don't know whether they know this project before. And when we launched, we realized the 2 projects are quite similar, and we have some interaction actually just in Seattle at the August of 2015. We have first meeting face to face to talk about the collaborate between the 2 projects, and in 2016 and 2017 we have more and more collaborations, and finally we decide to merge the two projects into one. And the KataContainers project is announced in last year, just like I say, the last December in Austin. And in May 2018 this year in Vancouver, we announced the release 1.0, and currently we are at 1.4.0, and that's released in last month. And right now we have about 6 weeks release schedule, and that means we will have the next release in about the end of this month. That will fall into the Christmas holidays. So maybe after the New Year, at the beginning of January, we will release the 1.5.0. In the past half a year, we have added some more features such as hot plug and the template and VSOC support and the multi-architecture such as the ARM and the Power and the S390X, and also have some improved devices support such as the GPUs. And currently we have the Containerd shim v2 support. This patch have already been merged in to the master and will released in the 1.5.0, and later we will have the demo for it. And also we have the Intel new mill as a new VMM to be support. Actually, after the AWS announced the Firecracker, we are talking about to have the support of the Firecrackers, and that's an interesting topic, but not the point of this tutorial. And also we are talking about some more hot plugs and left upgradings. Some of them may be released in the 1.5.0, and some of them may be in the further releases. And if you want to try the Kata containers, right now we have built some pre-built packages that pretty easy for you to do the integrations, and just over there, yeah. We prepare some postcard, a little bigger postcard, and there is some short instruction for run Kata, try Kata. So we have about maybe 10. So if you are interested in this, and you can have this card after the session. And also we have a booth in the exhibition hall, the booth IS17, I think. So you can visit there, and sometime I will be there, and there are other upstream developers there, and you can talk with them. And this is for the Ubuntu, so you can just use full command line to install the Kata into the into your Linux host, Ubuntu. Where's my mouse? Huh? What? Here. Okay, give it some time, and you can just use these four command lines to just get the source from the for the Kata, and to use the apt to install the packages. And actually, there is maybe even simpler. Actually, when I prepare this tutorial, I try to install a new virtual machine for the demos. When I install it, I found there's some amazing things. When we install the Ubuntu 18.04, and I found there is a page for some server snaps. They use snap. They have a KataContainers option. You can have the KataContainers with snaps. But for me, I'm not an expert of the step, but I think at least 15 years for the apt. So I like the apt things, and I will show you. Okay. So when we use the command line I mentioned before, we will have some Kata packages. Right now, in the source, there is some 1.4.0, and we do the packaging things. And once we release that, and the source will be updated, and you can just install them. Also, we package a guest kernel for it, and later we will upgrade it to 4.19. So, let us run something. Here in the Docker configuration, we add a runtime spec for the Kata containers. It will call the Kata runtime. Then we can use the Kata runtime to launch the containers. And okay. We can just specify the Kata runtime for the container, and yes, here it is. Yes, that's just like normal containers. You can't tell the difference from the runc. Yeah, so.
Can you run ps -ef?
Sorry.
BusyBox.
The BusyBox. PS?
Yeah, I want to see what is process running on.
PS.
Yeah. In the BusyBox.
PS.
Okay. Right now, I just detach it from the container. I will PS outside first. Okay. Here we find some interesting things. Yes, there's about one line for the container shim, and one for the QMIL, and one for the Kata proxy, and one for the Kata shim. So many processes in the host, and later we will show something different. Yes, this is inside. Inside, there's no exception. Yeah, just like you use runc and use Docker, that you have only the PS inside, only PS and the shell inside. Yes, this is the get start part. So that's pretty easy, and later we will do something for the connection with the Kubernetes. And so where is our slides? Yeah, here. And so after the introduction from the Kata side, we will from the other side to talk about how the Kubernetes reach the runtimes. I will shift the micro.
Okay, thank you, Xu. So in the last demo, which is very simple, but Xu just showed you how to use Docker to start a container by specify that I want to use Kata as a runtime, right? But in the real cases, we don't do that because Docker is basically a more complicated project. But what we want to see is we just want to use a secure container runtime, so we don't have to use Docker. And as we all know that Kubernetes is the most popular orchestration layer, so it's very straightforward for us to think whether we can use KataContainers directly as an alternative container runtime for Kubernetes. So we can just run the workloads from Kubernetes inside the Kata container. And then we can use this Kubernetes to build a very secure and highly isolated private cloud or public cloud, right? So we don't need to care about Docker stuff. But in order to use Kata container as a runtime of Kubernetes, the first thing we need to know is the CRI, Container Runtime Interface. This is a very interesting topic because CRI is actually one of the most important interface of Kubernetes project. I think you guys might heard about CNI, CSI, which is for networking and storage. And CRI is actually one of the earliest interface in Kubernetes project, which is used for the users to plug in different container runtimes inside of Kubernetes. And the story begins at, I think it's like 2015, when at that time, Chorus has a project which named Rocket, and somehow, for some reason, Chorus just tried to plug this Rocket as a Kubernetes default container runtime. They tried to do that, but eventually did not achieve that. But they succeeded to make Rocket as part of the Kubernetes code. So if you check the code of Kubernetes even today, you will see that there's a small package which is named Rocket, which is actually used by that time to integrate Rocket container in Kubernetes. It is actually a legacy problem. But then in this way, you actually have to literally maintain two different runtimes in Kubernetes itself. For example, I'm a member of Signode, so whenever we ship a new feature, which is related to container runtime, we have to think that, okay, this solution should work for both Docker and Rocket, right? We have to do that because the code is there. There's always a Rocket package in the Kubernetes code base. We have to think about it. But this is actually a very difficult problem for all the maintainers of Kubernetes because none of them knows very well about the Rocket project. So whenever there is a small problem, we have to seeking for help from Chorus guys. It's very difficult and actually make us very difficult to maintain Kubernetes. So based on this background, the Kubernetes community began to decide whether we can separate container runtime from Kubernetes. Then Kubernetes just care about how to create a pod, how to create a pod from the workload which the user delivered. And then we can use some kind of like client-server mode container runtime. So Kubernetes will essentially send a remote call to an underlying server, and this server will be responsible to create containers for you, to call Docker or to call Kata or to call anything that you want, like Rocket or something. So this is actually the basic idea of how or why we want to have this kind of CRI in Kubernetes. And Another reason is that I think you guys might heard about that from 2015 that Docker, the project itself, is becoming more and more complicated. If you compare the Docker the Docker today with the Docker project maybe 1 year ago, you just say Docker run something. You will find that today Docker run will consume a lot of more time than it was before. This, you can try it right now. It's the truth. It is because that Docker now has a lot of unnecessary part built into the project itself. So the Kubernetes community also noticed this problem because as Docker goes to this way, become more complicated, then Kubernetes have to rely on a lot of features of Docker, right? This is a very realistic problem at that time. So the Kubernetes community also think about how to decouple Kubernetes from Docker. For example, how can we make Kubernetes focus only a very few APIs of Docker, like create containers, start container, stop container, that's all. We don't need to care about this swarm or networking or any volume-related API of Docker. We don't even have to install Docker, maybe. So based on these two facts, and then there's another thing come, which is actually initiated by hyper.sh, which I also participate in most of this kind of period, because hyper.sh just created another runtime which named Runway based on hypervisor. So this container runtime is basically a small virtual machine, a lightweight virtual machine. Then how can we make this container runtime works with Kubernetes? This is more difficult than to integrate something like Rocket into Kubernetes, because it's essentially a different way. For example, how can you handle the host networking by using hypervisor-based runtimes? You have to deal with that from a very different approach, which is totally different from any kind of Linux containers. So with all of the facts here, the Kubernetes community finally proposed something which name at that time is the client server mode container runtime, and the first issue is actually created by Brandon Burns, and we talked a lot about how to make this client server mode container runtime as a default container runtime in Kubernetes instead of Docker or Rocket or Hyper or Runway or Clear Container. So that is actually the very beginning of the story. And after that, the leader of Signode of Kubernetes project, whose name is Dong Chen, he says that the Kubernetes should not vendor a runtime implementation. That means she is thinking that Kubernetes should not have a default container runtime. Right? So Kubernetes does not need to care about container runtime. They just need to care some kind of interface. That's enough. And that is why the developers from Google, Quest, hyper.sh began to, they co-proposed a design which name is Container Runtime Interface. So this CRI thing is actually a gRPC interface. And with this interface, your kubelet, whenever kubelet want to create a container, it just sends a remote gRPC call to the underlying runtime. But of course, there should be some gRPC server to serve your gRPC call from Kubernetes. I will explain it a little bit later. And the reason we choose gRPC is very simple, because this is kind of like a 2016 to 2017, and it is actually the first time that gRPC began to be open sourced, and there are a lot of adopters begin to think about it. And we also did a lot of benchmark. We saw that gRPC can improve the performance between the client and server mode, especially compared to the normal HTTP request. That's why we choose gRPC interface as the baseline here. And then we'll begin to write code based on the design of CI. And the first implementation of CI, which name is Docker shim. I think you guys might heard about this project. It is actually a built-in package, a built-in container runtime in Kubernetes. You can find this package in Kubernetes. And this package, which named Docker shim, is exactly the implementation of CI interface for Docker. But the reason we build in this server inside Kubernetes instead of just run a separate Docker shim on the physical machine or on the node is that at that time Docker is the only choice for most of the people. So we don't want to make Kubernetes installation very complicated. You need to install Kubernetes at first, and then install a Docker shim, and then install Docker. That will be too complicated. So we choose to keep Docker shim as part of Kubernetes. But today, we begin to talk about how to separate Docker shim from Kubernetes. So in that case, the Docker shim will become just like the normal CI implementations. And soon after Docker shim was implemented, we began to create another project which named the Frankty. And Frankty is the first non-Docker CI implementation, which focuses mostly on the hypervisor-based container. So you can think about that Docker shim is how Kubernetes talk with Docker. And Frankty is how Kubernetes talk with the hypervisor-based container runtime, like Runway or Clear Container at that time. So I will give you a little bit more detail about how CI design works. So In Kubernetes is actually a cycle loop. The cycle loop means it is an infinite loop. It just continue running and running. And Kubernetes is running a loop to do what? It actually watches the change of pod in the API server, aka in etcd. And whenever there's a new pod is scheduled, then the Kubernetes will notice that, okay, there is a pod in API server that is changed, because whenever Kubernetes schedule a pod, it will set the node name of that pod to a specific node. And then the Kubernetes notice, okay, this node name is exactly the same with me. So this Kubernetes will fetch this pod from API server to its local cache, and then begin to create all the containers defined in this pod. That is how the cycle loop works. And of course, this cycle loop should never be blocked, because it needs to continue checking and checking. So any kind of time-consuming operation in the cycle loop will be deferred to another Go routine, or we use some async ways to do things separately. We start several workers or like that. For example, Kubernetes will never mount volume directly in this step. We actually mount volumes in a separate Go routine for you, and Kubernetes only check if this volume is ready or not. Okay, so this is cycle loop. And whenever cycle loop found that we need to create a pod, then it will actually call a generic runtime. Generic runtime is a fake container runtime inside Kubernetes. So Kubernetes do not know which container runtime is running on your node, so it just called generic runtime. And the generic runtime will transfer your pod API object into the real CI interface call, a remote call, a gRPC call. For example, there will be an API which is like create container. That is, the Kubernetes will call the CI interface to create container for you. And we also have a definition like sandbox. A sandbox means how you implement a pod. For example, if you are in Docker, you actually do not have to implement the pod. The only thing you need to do during the create sandbox phase is you just create infra container, which name is the pods. I think you guys might heard about this container. It's very small. It is always the first container created when the pod is created, and this container is used to hold the network namespace of the whole pod. That's all. So when you have the CI, when you have the interface like this, then it is totally your business to decide how to implement every gRPC call here. That's why we have so many CI shims right now, like Docker shim, like Creo by Red Hat, like FrankT, like CI Containerd, and everything here is actually CI shim. So from this example, you can actually see what is CI. So CI is actually an interface that describes what Kubernetes expects from container runtimes. So that means Kubernetes only care about this very limited number of API from a container runtime. No matter it's Docker, it's Rocket, it's Cryo, it's Containerd, or even it's a virtual machine like Kata. Kubernetes do not care about that. As long as you can provide this limited number of interfaces to Kubernetes, it works. And we also decide to design CRI as a container-centric interface. So we do not have a pod, the concept of pod, in the CRI interface. That's because pod is a Kubernetes-related concept. We cannot expect the container runtime understand this concept, like Docker. Docker has no concept of pod. So we cannot say, hey, Docker, just create a pod for me. It's impossible. That's why in CI, we introduce another concept which name is sandbox. That means, okay, whenever Kubernetes create a pod, I will call CI to create a sandbox. But how the CI shim or the implementation created this sandbox, it all depends on you. You can just ignore this API. You can do that. And I think the key word of CI here is that extensibility. We want to make sure that the maintainer of container runtimes like Docker, like Containerd, they have totally freedom ways to implement their own CI shims for Kubernetes. And even if you are just a normal developer, you want to implement something which is not which is currently not ready in Docker, you can do that in the CRI implementation, because CRI implementation will then call Docker. So in this period, you can do a lot of things. You can wrap your API request, you can transfer the API request, you can do audit, you can do everything you want to do during the CI shim. Okay, so here's the question. How can I implement the CI? I will give you a very simple example. For instance, what we want to do is create a pod which name is full with 2 containers inside, which name is container A and container B. So whenever you use Kubernetes to create this pod, then what CI will do is like this. The first step is the Kubernetes will call the run pod sandbox full by using CI. Then your CI implementation will actually call the underlying container runtime like Docker or Kata or anything. But here is the difference. Because I said it's your freedom to implement the CI. Then you can make decision. For example, this run pod sandbox, what I will do essentially. If I was a Docker maintainer, what I actually do is create a very small infra container, which name is pods as I mentioned. So that is basically what Docker shim is doing today. It will create a very small container for you. So this infra container will always be the first container in a pod. But if I am using KataContainers, what I will do is totally different. In this step, I will create a lightweighted virtual machine, which is actually implemented by KataContainers. So there will be a real sandbox, which named full in this step. It's a lightweight virtual machine here. So it's totally different from Docker. And then Kubernetes will call the rest of the APIs like create container A and start container A and then B. And in this step, again, it all depends on you how to implement these APIs. For example, if you are using Docker, then you will actually call Docker API to create a container A and a container B for you. It's very simple. But if you are using KataContainers, then you don't need to create new containers because there is already a small virtual machine running, which name is full. And what you need to do is create 2 containers inside this virtual machine. But these 2 containers are just very simple containers with mount namespace. So it's not a real container. It's just a separate namespace with separate root FS. So this step is very different from Docker. But again, Kubernetes never know about this kind of difference. And the Kubernetes only know that, okay, I just create a pod, and the pod runs all the way through its life cycle. That's all. That's why we want to have the CI implementation here. And another thing you need to think about, sorry, yeah.
So one question.
Mm-hmm.
So in Docker, we have image repository, which is the Docker hub. How about KataContainers? Does it use the same Docker hub?
Yeah. KataContainers is only different for the container runtime part. It uses hypervisor to replace namespace and the C groups. But for the image, it's totally exactly the same Docker image what we are using today. Yeah, totally the same.
Like Docker has a swarm for clusters. Does it have this KataContainers for later time?
Yeah, what? Sorry?
Docker swarm is there for Docker, right?
Yeah.
Is it anything available in KataContainer or just?
Oh, I see. So if you want to use Swarm, it should work with KataContainers, but there will be some features which is do not work. Because Swarm has its own concept, it relies on some special functions of Linux container to implement, like service.
Yeah, let me answer this question. And your question is about could we run Swarm with the KataContainers, right? Actually, most of the part that works because the Kata runtime itself is just a container runtime. And the only part is about the networking part, especially about the DNS part. And there are some workaround for that. I can't say that the implementation is clean, but yes, we can hack it to support that. Yeah, that's the case. And now we will go on the CRI part.
Yeah. So I just mentioned the first step you want to implement CRI is about how to implement the pod lifecycle. And the second part you need to implement is the streaming server, streaming API. What is streaming API? It's like logs, execute command, attach. These are all streaming APIs. So streaming API implementation is very different in Kubernetes. I'll give you another example here. For instance, if we want to do a kubectl exec to a pod, then your API request will be sent to API server, and API server will directly call Kubernetes to do an exec operation. And then, as I mentioned, Kubernetes will call CI exec to your CI implementation. But at this time, the CI implementation will not call Docker or any container runtime directly. The CI implementation just return the URL of the streaming server. So the streaming server is started whenever a CI implementation is started, because Kubernetes provided you with a standard library to implement the streaming server to respond to any streaming API. So in this time, you just return the URL back to to Kubernetes, and Kubernetes return it all the way back to the API server, and retriggered a redirect request, which sent to the real streaming server running on your node. And then the streaming server responds to your streaming API like logs or exec here. The reason we designed like this because we found that Kubernetes will be actually very busy if there are a lot of streaming APIs, like a lot of customers or a lot of clients that are doing logs or exec, then Kubernetes will actually die or crashed. So we separate all the streaming API to a separate streaming server here, and in Kubernetes it can use a independent state group to wrap a streaming server inside a isolated environment. So the Kubernetes will be fine. Okay, so that is a CI implementation, and I think I will let Xu to explain more about how to integrate Kata with Kubernetes.
Thank you. Yeah, we will go back to to connect the Kata containers with the Kubernetes. First of all, we will think about the Docker shim and the Docker part. Maybe we could just put the Kata runtime to the Docker's position, to the run sys position. If we use the Docker and to call the Kata runtime and get the shim and to do the connection. And just minutes before, we have show you all the processes of this case. Yes, so many processes: the shims, the proxy, and something else. But unfortunately, this doesn't work well for Kubernetes. Actually, there is a small trick about this one. That's about we should let the runtime should let Kata know this is the sandbox, and this is the container inside the sandbox, and something there is some info for the runtime. But right now the Docker doesn't support to pass the annotation to the runtimes. It processes all the annotations, and it won't pass the annotations to the runtimes. And there is some patches submit to Moby, and that's still pending there for half a year. So from the Docker, there's no direct way to support that if you don't apply some off-tree patches. But that won't be a big problem. Right now, you can use the containerd itself. Actually, the containerd, we could use containerd because it's already support CRI. The CRI have a plugin have been part of the officially part of the containerd release. So we can use the containerd to call the Kata runtime, and get the containerd. Firstly, containerd will create the containerd runtime, a containerd shim, and the this is for the decouple things, and Kubernetes shim will call the Kata runtime. And once Kata runtime will create the sandbox and the proxy, if that's required, and create the Kata shim and shift the Kata shim to the Kubernetes shim and run this. It works, and but not so elegant actually. Yeah, you have already seen the processes for that. If you run the Kubernetes use the Kubernetes and Kata, you will have the Kubernetes shim process and the Kata shim process and the proxy process and the sandbox process. So many processes in your host. Though it works. And one more thing is about the proxy. Here it's surrounded with the dashed lines. Actually, the proxy is not really not the essential one. If the container itself supports the so-called vSock, then that's the proxy is not could be omissed. It just depends on the host kernel. If the host kernel supports vSock, then the vSock works. Yes, I say that's not so elegant here. Actually, years before, we have the RunV project, and with RunV we have a Fractive here. And they just mentioned that the Fractive is the first non-Docker implementation of CRI. And through the Fractive, and we call through gRPC to call a process called a daemon called hyperD, and it has the RunV built in, and the RunV will create the sandbox for the Fractive and for the kubelet. And in this place, if we use the Fractive instead of the Kubernetes, we can have the only one Fractive in the machine, and only one hyperD process in the machine, and the others for just one process per sandbox. So no more process. And so that sounds good. And the only thing is we can try to make these things become a plugin for the Kubernetes. Then that may lack the structure to be more elegant. But wait, there is still a problem here. If you want to support more runtimes, and that may not work. If it become a Kubernetes plugin, then if you want to use the other plugin to run the runC container in the same host, that's not easy to implement it. That may need some architecture change for the Kubernetes side. So that sounds not so good for the community. And fortunately, we are not the only one found this issue, and the upstream Kubernetes upstream want to solve this problem as well. And here we can state the problems here. Actually, the main problem here is about the shim. There is a shim between the Kubernetes and every container. Actually, even with runC, there is a Kubernetes shim for runC. The Kubernetes itself, the shim itself is just to react the process of the container, and they can decouple the Kubernetes daemon with the running process of the containers. So if you upgrade the Kubernetes, or the Kubernetes itself is crashed, and you don't need to that won't affect any running containers. So the things here is try to doing the things decouple with an indirect layer for the Kubernetes. This is a good point, but the problem here is the Kubernetes shim itself is always always think the container runtime is runc. And that means your container, your runtime should have a command line that's compatible with runc. Here, has a runc command line. That's why the Kata runtime is try to implement what runc implement. But things is the runc command line itself is not standardized. There is an OCI specification, you know. The OCI is try to be an open standard for the container community, and it has two parts of the specification. One is about the runtime, and the other is about the images. But for the runtime parts, they have a JSON format specs and some definitions, but no command line specs. And I think last year, maybe the year before last year, people are talking about the command line standardizations. But until now, the command line is not standardized, and all the people try to give up these efforts because we have a better candidate. And moreover, every runc container is a process, you know. Just because that's the container. It's a process and maybe a process group, a C group. That means if it's a process, then it must have a PID here. So the process ID. The PID means match. At least you can kill it, right? You can use kill to send a signal to it. To the hub. The hub is the most commonly signal, and also sig kill, sig term, and other signals. And that means if the container is not a process, even if it's not a process, it should support these features. Just like Kata. In Kata, we use the VM as a sandbox for containers. That means the sandbox is a pod, and there may be container inside the pod, maybe multiple container inside the pod, right? If we have 3 containers inside the pod, but in host there is no process for each containers, right? And if it's assumed as a runc container, then it have a PID for them. And it could send the signal to the container, to the PID, and to kill it. But here, we cannot know which process to be killed. That's the case. So we have to implement another process called Kata shim that have a PID. When it get the signal, and it will forward the signal to the process inside the sandbox. This is the only responsibility for this process. It looks quite tricky here, and actually we don't like this implementation. But whenever you must have the runc compatibility, you have to implement this one. So here is a stub process to forward it. That's a shim. You know, firstly there is a container D shim, and then there's a Kata shim, a 2 shim for 1 container, and not 1 sandbox for 1 container. So once you have a sandbox, and once you have a sandbox and several containers inside the sandbox, you have maybe you have n+1 shims for 2 times of n+1 shims for the pod. That's a bit terrible, right? Yes. That's make me recall one famous quote. In the computer science, every problem could be solved with an indirect layer, except the problem of too many indirections, right? Here is the problem, too many indirections. And fortunately, the Google and Kubernetes folks, they also realized this problem, and they are very smart to propose a very small change to fix this issue. A small change, and it's make a lot of difference. The change here is they get the shim socket URL from shim invocation. Instead of to pass it to the shim, for the version 1 of the shim, when the container creates the container shim, it will pass a unique local socket address to the shim, and the shim will serve on this address with the interface. Then that means every container should have an independent address socket. And if they give in the V2 case, the shim could, when you call the shim without such an address, the shim will have their own address and return the address back to the container. That the change is the shim itself will decide which address to return, and several shim may return the same address back to the container. In this case, we could address if we launch containers inside a single sandbox, then we could all the sandbox could return the same address back to the container. So there will be only one container shim for all the sandbox, and no other process, no independent kata shim here. So instead of 2 times of n+1 shims, we have only one shim for one pod. And the things could be even better because the PID means little now. That means they don't depend on the PID itself to do the kill and signal things. They just call the interface provided by the shim v2. The canary call this socket with some gRPC calls instead of try to kill the PID. In this case, even with one shim for all the sandbox, there are no problem for that. The PID is only an ID here, not a process. So that was to implement a new simple shim for the kata. That's we could provide one fewer indirection layer, right? That's the most hard things in computer science. Okay. Here the case of the Kata containers, and from the 1.5.0 we will have the Kata shim v2, and this patch implemented by my colleague Fu Pan have already merged 572. The implementation is submitted at July and finally merged in November. Yeah, almost half a year. We do many reviews and many fixes, and including some of the refactor of the Kata runtimes, and it's merged and will be released. And there is some small patches on the way to be merged, but that's all small fixes, and we will get them to be merged soon. And with this case, you can see we have a pretty simple picture now. The picture is too small compared to the prior one, so I have to add so many words here. Here is a gRPC call, and then we will call the sandbox. There is one container shim v2 for one sandbox. Yeah. Okay. The demo time. Let's come back for the demo. Yes. You know, we have container inside my my virtual machine, and actually I use the latest containerd. In the user local, that means this is not an distributed one. That's my personal build. That's from the master branch of the containerd, the latest one. But I didn't change it. It's just from the official repo. And for Kata. This is the Kata runtime, and this is some small fix. I said some small fix on top of the master, and quite small fix, and the fix will merge soon. And here, just to make, you could have the condition Kata v2 and put this into your path, and it will work. And if you want to run it with the CTR, that's if we want to use with the CTR, you can just with the simple command line to provide the runtime io.containerd.run.kata.v2, and that's the naming pattern. We'll find our containerd shim Kata v2 binary. That's the naming pattern, and you can run it busybox.
So this is already compiled.
I have already compiled it and put it to the user local bin. Yeah. Yeah, here. And yeah, run here. Again, I will show the process. This process is the CTR ones, and the first two is the CTR, and the third is the runtime v2, and the fourth one is the sandbox itself, and no more other process, no other shims, and no proxies here. So there's only one process here, and yes, I will do something more, and before that I will tell you some new facts. And yes, what we could get from the shim v2. And firstly, we have much fewer processes, and this is really appreciated. And almost everyone like this feature. Nobody like too many shims. And last month we have a forum in the OpenStack Summit in Berlin, and there is a forum. And in this forum, I said I hate shims, but our committee member Samuel, he said he loves shims, but he don't love too many shims. So this one we both like this one, and only one shim for one sandbox and no more other shims. And this is the part for the containerd. Some of you may use the CRI here, and for CRI, they are going to support the containerd shim, the shim v2 interface as well. So at that time, from the containerd, from the CRI side, this will become true as well. And when we do the node conformance tests here, and only 4 cases are failed, and all others have success. And the 4 is at least here, and this 4 all depends on the host network. That means put the sandbox inside the network namespace with the host. That means share the same namespace with host. That means make it as a system, a container in the host system. And this breaks the isolation for the sandbox, and that's not supported by design. It's not a bug, it's a feature. So all the things are supported. And before that, before we close, we can show you some more tests about how we use it with the CRI. Here is the configuration of the containerd, and in containerd we have some other things, and the most important thing is about the plugins part. And here we have the CRI plugin and the default runtime of the CRI plugin, and here these 2 lines works. And now the current configuration is the V1 version 1 of the shim, and then it will call the Kata runtime. This is the old one and the already exist one. And I will test with this one, and later I will change it to this one to test the V2. And the test case is about the time, the time to launch a container. And the tool is here. Here is the CRI tools, but this is not the upstream version. Yes, my colleague Fu Pan, and he did all the awesome works. He implemented the shim v2 and also implemented the benchmarks. And here is the benchmarks, and there is some benchmark for the container operation times and the pod launch times. I just comment some lines out to have a faster demo here. This benchmark will call the CRI interface through the CRI interface to call containerd, and the containerd will call the Kata the shim and to launch the Kata containers. here I have already built the CRI test and specify to the benchmark and to run on the containerd socket. So the test is try to use the CRI interface to call the runtime and to launch pod and launch containers. It will repeat the operation for about 20 times and get the mean time and the standards deviation of the time. And right now I use a local virtual machine on top of inside my laptop and with the nested virtualization support. So the speed is not so fast, and for the demo, I just comment out some of the cases to make it a bit faster. Yeah. Let me go back. This time is about to create the sandbox and create a container inside the sandbox. So that's the normal case for a single container pod. And the container, I think, is just a busy box. And the fastest, for the 20 times of the test, the fastest one is about 1 second and 800 milliseconds, and the slowest is 2 seconds and more than 1400 seconds. And the mean time is almost 1.9 seconds. And this is for the shim v2, shim v1. Yes, and this is also other tests about only create sandbox and only do some sandbox operations and stop sandbox and remove sandbox. And I just comment out other tests to save time here. Yes, we have restarted the container. The start is too fast, so I can't stop myself to check it again. And now we repeat the test. Yes, it began with the shim v2, and let the test run. We will show the other slides to save some time. Yes, and actually, when we support the shim v2, we will have the much shorter time for the container boot. And this is for the baremetal case, and this is for the nested virtualization time. And if for nested virtualization, this will be more. it's more easy to find the difference. And with the direct use the Kubernetes runtime, use the Kata runtime, compare with the shim v2, will very significant difference. And with the when you use the baremetal, when you use the shim v2, that will very close to the RunC itself. And also there's one more thing about shim v2, because actually for Kata in the production usage, the pain point is always be the storage. If you dig into the project deeply, you will find this. And there are many critics on the 9pfs support. Everyone want to put it into production will talk to me still about what do you think about the storage part? What do you think about the 9p? And we had to say if you want to put it into the production, you have to avoid to use 9p for the serious part, especially for the storage-oriented applications. It's not only because of the performance part, but also the 9p has some problem on the POSIX semantic compatibilities. Sometimes it will break some POSIX semantics, and we have to do some dirty hack to make the APT and other things run well. Also, because the 9pfs, the implementation itself is not so good, and in the QEMU, so sometimes there is some security bugs about the 9p. So we have to avoid to use it for the production environment. So for Kubernetes, the case is snapshotter will pass the mount structure to the task plugin, actually the Linux task plugin, and the shim will mount the file system and then pass the file system to the runtime. And for the V1 case, we cannot do anything. We just accept. We can only accept the file systems. And if you want to pass the block, even with a block-based storage snapshotter, you have to accept the file systems, and you have some choice. The first one is you use 9p to pass it into the guest, and then the second one is you try to unmount it again. That's the shim mount it and the runtime unmount it and pass it to the guest. That looks very ugly, and sometimes the host itself assume the shim have mounted, so they break some assumptions and maybe lead to some problems. But if you don't unmount it and just pass the block device, if you think that's a block device, then both the host and the guest have the right access to the file systems, and this may break the super block of the file system. That's the worst thing. So there's no clean and good implementation for this case. But in shim v2, now we can handle the storage by ourselves, such as the mount passed to shim v2, and shim v2 can decide to mount it or not. So we can, if it's a block, we can just pass the block to the VMs. Then this makes things better. Yeah. And let's go back to our test. Where is? Here. It should be no difference? Okay. Bingo, I got it. Okay, almost the same. And I think there's a little bit better, and I think at that time the bad for the V1 the worst things is 2.4, and the mean time is about 2, 197 or 190.
Right.
Yeah. So a little bit better, and there is always happen some things when people do demo, you know, and this time is not very bad. At least it's become better. Right? It should be much better, but for demo, you know, there's many things you can't handle it, and that's the last page. And Kata is a fully open source project and hosted by the OpenStack foundations. And we are not an OpenStack project, but also we are an independent project. And all the code and the documentation is on the GitHub, and we have the Intel and Hyper have the initial contribution, but the project is under Apache license, Apache 2 license, and we have an open governance about it. So every week we have the architecture meeting. So we are in open developing status, and any contributions are welcome, and our Slack and IRC and mailing list are welcome everybody to join. So if you have interesting, and here's some tips for getting started, and also you are very welcome to do any kind of contributions, and thank you very much.